Hello and welcome to Bitcoin Explained, where I break down some of the technical aspects behind Bitcoin in a simple way. In this video, we'll be talking about elliptic curve cryptography, which is the cryptography that Bitcoin uses. This is actually the fifth and final video in a 5-part series on the cryptography behind Bitcoin. In videos 1 through 4, we talked about finite fields, we learned about elliptic curves, we saw elliptic curves over finite fields, and then even learned about the specific curve that Bitcoin uses. In this video, we'll be building on all of that prior knowledge and actually talk about how we sign a transaction using the private key and are then able to verify it using only the public key in a way where we know for certain that the private key was used to sign that transaction without ever revealing the private key. This is really interesting, really cool, and once you understand this, you understand why transactions on Bitcoin are so secure and how private and public key cryptography actually works. So with all that said, let's talk about elliptic curve cryptography. This video will be split into 2 parts. In the first part, I'll be doing something that I usually don't like to do, which is draw some formulas on the whiteboard and explain them. And in the second part, we'll be walking through the formulas step by step using a real-life example by me sharing my screen and walking through a little bit of code, which will be really easy to follow along. Now, the reason that I'm doing it this way is because I think for this topic it's actually really important to understand the formulas first, which really aren't complicated, but you just need to have seen them and understand the logic behind them. And then once you see the real-life example, this will become super clear. And then by the end of the video, you will have understood elliptic curve cryptography, which everybody thinks is a super complex topic, but it doesn't need to be that complex. What we'll be talking about in today's video is what's called the elliptic curve digital signature algorithm, ECDSA for short. This is basically just a sequence of steps that you follow in order to produce a digital signature on an elliptic curve or using elliptic curve mathematics with your private key that can then be verified using your public key by anybody in the Bitcoin network. This process is basically split into 3 parts, which I've written down here. So we start with the key generation, so how you actually generate your private key and your public key. Then you create your digital signature, and then you need to be able to verify that signature as well. Or in this case, it doesn't need to be you, but it needs to be everybody else who needs to be able to verify. So I'll just be walking through each of these step by step and explaining how we get from here to there and then prove that all the mathematics actually works. So key generation. We touched upon this in the last video already, but if you remember from the last video, a public key is generated by simply point multiplying the generator point that Bitcoin uses with the private key. Now this just looks like the following. So we've got the public key Q, which is simply equal to D, which is the private key, point multiplied with the generator point, or the generator point multiplied with the private key. Now remember, the generator point G is publicly known and its X and Y coordinates are the same every time we use it. So everybody in Bitcoin uses the same generator point. This is really important because computations need to be reproducible and deterministic, which is guaranteed by doing this. Now also remember the private key D is essentially just a really large integer that is securely and truly randomly created, and that you or whoever creates it keeps secret, so nobody else can know about this private key. And then your public key, which is Q here, just becomes the generator point multiplied by the integer that is your private key, and that then links to another point on the elliptic curve, which is your public key. Okay, now that we have the public key, let's talk about how to actually create a signature and what we're signing. So in Bitcoin, what we're signing is what's often referred to as a message, but in this case, the message is just a transaction. So in the end, basically what happens is that when you create a Bitcoin transaction, the information about that transaction, such as where the Bitcoin that you're deciding to send to another address is coming from, as well as how much Bitcoin you're actually sending and who you're sending it to, so which address or multiple addresses that Bitcoin is going to. That's all converted into a standardized format, which is just, in the end, technically just a string of bytes, which is your message. So basically, the message that you're signing and the signature that you're creating is just the signature of a message, which in the end is just a string of bytes that describe the Bitcoin transaction you want to send. So that's the first thing. So we have the message M as our input that we take, so to say. And we then go through a few steps. So the first step is to create a hash of this message, which is to compute what's called Z, and that's computed by doing basically a double SHA-256 of this message M. Then the second step is to generate a securely and randomly generated integer k, often also referred to as the nonce. So we generate k, and k in this case has to be, let's put it here, greater than or equal to 1 and less than or equal to n minus 1. Now remember, n in this case is the order of the generator point that we use. So k has to be between 1 and the order of the generator point minus 1. If you remember from the previous video, you'll know why this is important. Then, after we generate k, what we do is we compute a point on the elliptic curve using k and the generator point. We're calling this point r. R is equal to the generator point multiplied k times. Now remember that k is a securely, randomly generated integer, and it actually, one thing that's also really important is that this randomly generated and securely randomly generated integer k, the nonce, is recomputed every time. So you never ever reuse this nonce k. This is really important because otherwise later on in the process, if you ever were to reuse k, a malicious attacker could basically backsolve for your private key by observing that happening, but that's another story. So we create this point r, and then in the fourth step, we just get small r, which is essentially just the x coordinate of r modulus n. The modulus n we just do to make sure that this integer, because remember r is just a point on the elliptic curve, so it'll have an x and a y coordinate, and because we're doing elliptic curves over finite fields, we know that this x coordinate of r has to be an integer, and by doing it modulus n, we just make sure that it falls within the valid range of integers. Then we compute one other thing, which is s, which is equal to the inverse of k multiplied by z plus rd. Now, this might seem a bit complicated, but this basically is just another integer that combines k, so this random integer here, as well as the hash of the message, and also this point r here and the private key. So it links all of these components together. Now, let's think about why we want to do something like that. So, as I said in the beginning, the whole reason why we want to do this whole process is that in Bitcoin, we want to be able to transact on the network in a trustless fashion, meaning that there's no centralized party, there's no controlling party that we need to trust to verify transactions. There's no middleman, there's no bank in the middle that will tell us if you want to send a transaction to someone else, that you actually have the Bitcoin and that Bitcoin is then correctly sent to that other person. We want to be able to do all of this in a completely decentralized, trustless way. So what we essentially want to do is we want to be able to sign a transaction using the private key here, our secret integer. And then later on in this step here, which we'll get to in a second, we want to be able to verify that the signature that we end up with in the end, which I'll talk about in a second as well, was actually created using this private key. But because this private key is what gives you ownership of Bitcoin, this can never be revealed to the public. So how do you actually prove that you created a signature using this private key without ever revealing this private key? The only way to do that is to use the public key, which is linked to the private key, and by doing this mathematics, which introduces some more randomness using k, and then constructing these variables in a way that they are linked to the private key, the message that we're sending, and another random integer. And then we can see in the next step how we can use all of that to actually verify that the signature was created using the private key without revealing the private key in a way that only the private key could have signed that message. Okay, so let's get back to this. So we've now computed S as well, and then the signature just becomes R and S. So we then have the signature which is just R and S. That's how we create the signature. Now, once we have that signature, what we do is we can broadcast the transaction out to the network, and we can include the transaction by definition is included because you're sending the transaction out. So anybody will be able to create the hash of that message, which is just the transaction. And then within that transaction, we include the signature R and S. So they basically become publicly available as well. And we will use all of that in the signature verification step above. Just before we move on, I just realized that in the final step, step 5 here, the computation of S technically also has to be done modulus n. This is once again just to ensure that we stay within the range of allowed finite field values for our elliptic curve over the finite field that Bitcoin uses. Now, moving on to the verification of the signature, we now know that the following variables are all publicly available and known. So we have Q, which is the public key corresponding to the private key that was used to sign this transaction. We also know all of the important variables or parameters from the Bitcoin curve. In this case, we know the generator point G, that's the same for everyone. And we also know the order of this point N. We also know Z, which is equal to the hash of the message or the double SHA-256 of the transaction that is being sent. And we also have R and S from the signature. Now, using only this available data here, we will now walk through how we can use all of that to verify that the signature was indeed created using the private key. So the first step is to check that R and S are valid, which just means that R has to be less than or equal to 1, has to be greater than or equal to 1 and less than or equal to n minus 1, and the same for S. One important thing to note here is that at any of the steps in the signature creation, if R, for example, is equal to 0, then we need to go back to step 2 and generate a new securely randomly generated nonce K, and the same goes for S. So during the signature creation, we already kind of checked this. So R and S can't be equal to 0. But then in the signature verification, that is actually the first step that we do, is making sure that they actually fall within the range of values that we are allowed to have for any of the mathematics that we're doing here. Then the second step is to compute the inverse of S. We'll just call this W. So W is equal to S minus 1. Remember that S is this down here. Then we calculate U1 and U2, where U1 is just equal to Z multiplied by this W, and U2 is equal to R multiplied by that W. Now, we will be using this U1 and U2 to actually reconstruct this point R here in a really clever way in a second. So that brings me to the fourth step, which is to actually reconstruct this R, but we'll call this R apostrophe, where we do U1 multiplied by G plus U2 multiplied by Q. So what are we doing here? We are trying to reconstruct this point here that we generated using the random integer, the nonce k, and the generator point. But instead of using k directly, because remember, throughout this process we created R and S includes k, and R in a way includes k as well, but k is not publicly known. K is another secret integer that we have. So we have two secret integers. We have D, the private key, and the nonce k. Both of those have to stay secret and only known to the person who creates the signature. So what we do here then is we try to recreate R, but without directly using k, using the generator point and the public key through this U1 and this U2, using the message hash and the x coordinate of R that we computed up here. And then basically what we do is, once we compute that, which is easy to compute because we've got all of the variables available, we just get what we will call R small r apostrophe, which once again is just R apostrophe. So the x coordinate of this new R modulus n. And what we then do in the final step is we check that this newly computed small r is equal to the R that we got in the signature. If this is the case, then this is a valid signature, and I'll explain why this is true in a second. So if R apostrophe is equal to, this is Python code written out, R, this double equal just means that two things are equal to each other, then we have a valid signature. If this is not the case, then the signature is not valid. Now, to prove to you that this is actually a valid signature verification, meaning that if we get that this newly computed small r is equal to the R that we received in the signature, proves that the private key was used to create the signature, we'll just rearrange the formula a little bit and then show that the result is correct. So at point 4 here we have the following. We've got R apostrophe is equal to U1G plus U2Q. Now remember that Q is just equal to D multiplied by G. So we can rewrite this as R apostrophe is equal to U1G plus U2DG. Now, what we can also do is we can replace U1 and U2 with the formulas that we had up here. And then what we get is the following. R apostrophe is equal to ZW times G plus RW times DG. I'll just put a line here so it's clear that we're not going over this and it's not too confusing. I'm sorry this might be a bit small, but I'm sure you'll follow along. What we can then do is we can group some of this together. So notice how we have G on both sides of the addition here, and we have W here as well. So what we can then basically do is we can just combine all of the common terms, and we can rewrite this as Z plus RW times RD times WG. Okay, but now remember that W is just the inverse of S, and S is equal to this. But if we just take the inverse of this, then what we get is the following. I'm going to omit the R apostrophe here now, just so we can write this all down. So what we then get if we replace this W with the inverse of S is we get Z plus RD multiplied by the inverse of Z plus RD, Z plus RD minus 1. And then also we still have K, or the inverse of K here, so we take the inverse of that, which is just, we'll write it as K minus 1 G. But what this essentially just is an element multiplied by its inverse, which cancels out to be the identity element. And then we also have an inverse, or the inverse of an inverse, which is just the original element itself. So this leaves us with R apostrophe equal to KG. And this proves that all of this has been constructed in a way where we recreate this point R that we created here without knowing K or D. So we've created a signature using this private key that we can validate using all of these available data points here. So the public key, generator point, the message hash, and the signature components R and S in a way that never reveals the private key or the secret integer K. Now that we've seen all of these formulas, we're done with the boring part of this, and let's look at a real-life example using Python code. Once again, I'll just be sharing my screen. I've created another Jupyter notebook, which just helps me visualize some of this stuff and have some Python code in here. You don't need to follow along with the code or understand what it does. I'll explain everything that's necessary to understand. But what's nice about this is that it allows me to go through the ECDSA algorithm step by step and print out all of the intermediate results. So we really see at each step in the whole process what is the result that we actually get, and then how does that convert into the result of the next step. And this will make it really clear, because going through everything on the whiteboard is a bit abstract, but this makes it concrete. Now, to start off with, I've chosen a relatively small elliptic curve, which is the elliptic curve here. Y squared is equal to x cubed minus x plus 1. And the reason that it's small is that I've chosen a small finite field that this will be over, which is a finite field of order 29. And then I've also chosen a generator point, which is this point G with coordinates 5 and 18. The reason that I've chosen this generator point is that it allows me to create every other point that falls on this elliptic curve over this finite field. Now what that looks like when we plot it on a graph is just the following scatter plot. Here we can see all of the points that actually fall onto this elliptic curve over that finite field, which is similar to what we saw in the videos on elliptic curves over finite fields. The generator point 518 is just the point here. Now remember that in order to create a public key, we had to first generate in a secure and random way an integer that is our private key, and then we simply point multiply, in our case this generator point here, by that integer, and then the resulting point, which will be one of these other points, the blue dots on the scatter plot, that will then be our public key in this example. So let's do that. In this case, I've just chosen an arbitrary secret that I'll be converting into the private key. So in this case, I'm just choosing the byte string of Satoshi Nakamoto, doing a double SHA-256, and then converting that into an integer using this code here. I then convert this secret into the actual private key by doing this resulting integer modulus n. Once again, we do modulus n in order to convert any integer value into a valid integer, which in our case means an integer or finite field element that falls within the range from 1 to n-1, because with the finite field that we're using here, this is the value that's allowed. Then we compute the public key, which is simply the generator point multiplied by the integer that is our private key, which we'll see in a second. And that's already all of the key generation. So let's look at what that actually looks like. So I'm also printing the value of the private key down here, which is just the integer 28. And when you point multiply the generator point, which remember was this point here, 28 times, then you end up with this point Q up here. So that is how we get from the generator point, which on Bitcoin's curve is shared and the same for everyone, to the public key using a private key that we securely and randomly generate. In our case, I haven't securely or randomly generated this, so don't do something like this in practice. But for the example, this is really reproducible and yeah, good for demonstration purposes. Now let's move on to the signature creation. So in this case, I'm just choosing a byte string of send 0.1 Bitcoin to Satoshi Nakamoto as the message that we will be signing. In real life, this would be the byte string that is created based on the information contained within an actual Bitcoin transaction, but for demonstration purposes, this is totally sufficient. What I then do is I do a double SHA-256 of this message once again, then convert it to an integer, do modulus n, and then we can see that in this case the message hash actually becomes 16. Now once again, just to really bring this point home, the reason why we always do modulus n in this case, and n once again is the order of the generator point, is that the resulting integer falls within a possible multiple of the generator point that isn't too big, meaning that it guarantees that we never wrap around after the point at infinity, which we talked about in the previous video. And yeah, so we get a message hash, in this case just an integer 16. Then we generate a random integer k. Now in this case, I'm using the Python library random to just get a random integer between 1 and n-1. In this case, the random k that it chooses happens to be 26. Now, this library doesn't actually create random integers securely, so don't ever use it in practice, but it's good enough for this example here. Then the next step is to compute the point r, which is the result of multiplying this random integer k by the generator point that we've chosen, which results in the r11 4. So those are the coordinates of the point that we end up with, and we can check that 11 and 4 is the point here. That actually is a point that falls on this curve. Great. Then we get the r value, the x value of this r, which we can see from here is just 11. Once again, we just return that here. And then we compute the second part of the signature, which is the value s. Now to get s, we need the inverse of k, which in this case in the Python code is computed this way. You don't necessarily need to understand what's going on here in terms of the code. just know that this is getting the inverse of k, and then it's multiplying that by z plus r multiplied by d, once again doing the modulus n here, and we then get that s is equal to 21, which means that our whole signature is just a tuple of two integers, 11 and 21. That is our digital signature over this elliptic curve, in this case, signing the message send 0.1 Bitcoin to Satoshi Nakamoto using the private key that we generated. Now, just to really explain this point once again, why we do the modulus n, you can see that if you take just the double SHA-256 hash of the message and convert it into an integer, what you actually get is this integer here. Now the reason it looks like that is because SHA-256 converts anything into a 256-bit integer value, so it will oftentimes end up looking something like this. It'll be a really large integer value, and then the modulus n just converts that into something in the range of 1 to 36 for us. Yeah, that's just to really drive that point home. So I hope this is clear for everyone. Then we move on to the next step, which is the signature verification. Now the first step, as we talked about in the previous video, is making sure that R and S fall within the range of 1 to n-1, which I'm checking using these two conditions here. Both of those print to true, so they are valid values in this case, and as we saw, 11 and 21 do fall within the acceptable range of values. Then we compute the inverse of S, which in this case is just the integer 30. The math is being done here in the code. Once again, you don't necessarily need to understand this, but this just computes the inverse of S. Then we calculate the values u1 and u2. Once again, u1 is just z, so the hash of the message multiplied by this w, the inverse of s, and u2 is equal to r, so the x-coordinate of the point r that we computed earlier, multiplied by w. Both of them computed modulus n, just to make sure we fall within the correct range again. And then we've got u1 is 36, and u2 is 34. Again, all just integer values that we end up getting here. Then what we do is we reconstruct the point r that we computed earlier using g, so the generator point, and q, the public key, in combination with u1 and u2, and then print the coordinates of that point, and we can see this point is in fact 11 and 4. So we've ended up with exactly the same point that we had above. Now, getting v, I called this r apostrophe on the whiteboard, but it's the same thing. And then checking that this is equal to r. The reason I called it v here is so that we have a clear distinction between v and r, and it's not confusing, but it's the same thing. And we can see that they actually are equal to each other, as we saw just looking at the coordinates of the point, and we therefore have a valid signature. This is awesome. This is all it is. So to quickly recap before we move on to how this works on Bitcoin's curve is we just have these elliptic curve points here, a generator point, get the public key, then create the signature R and S components like this, and then just confirm that the recreated R, or the x-coordinate of that R, is the same as the original R. And because we are including the private key, the message hash, the random integer k, and the point R in the original signature, the only way that anybody could have constructed that original signature is by using the valid private key, because otherwise you can't mathematically compute R and S, especially the S part. So if this here prints to true, then we have a valid signature. Now let's look at the exact same process just on Bitcoin's elliptic curve. So As you might remember from the previous video, we've got all of these parameters here that define Bitcoin's elliptic curve. I've just put them all into code. So we have n, the order of the generator point, we have p, the order of the finite field, and we've got a and b, which is 0 and 7. Those are just the parameters that define the curve so that the equation ends up being y squared is equal to x cubed plus 7. Because a is 0, the x part of the elliptic curve equation form just falls away. Then we construct Bitcoin's elliptic curve using these finite field elements for a and b. We construct the generator point using the generator point x and y values. Then we get the same secret. Once again, Satoshi Nakamoto converted, hashed twice and converted into an integer. Modulus n once again. In this case, n is a completely different value, so we actually end up with a completely different private key. Compute the public key and print the public key corresponding to the private key, which we can quickly have a look at down here. So the private key, first of all, is this integer here. And then the resulting public key has this x coordinate and this y coordinate here. So once again, these are just integer, really large integer values. And because we're now using Bitcoin's curve, which is able to have way larger finite field element values than the elliptic curve over the finite field that we saw above of order 29, we get way larger values. So we've got that. Then we hash the message, again using the same message as above, but we'll end up with a different message hash because once again we're doing it modulus a different n. We get the random integer k, or the nonce. Again, the same method. Compute the elliptic curve point r, get the x value of r here, then compute s once again in the same way and get the signature. Now I'm printing all of the outputs, so let's just look at what that looks like. So the message hash in this case is this integer value here. The nonce, or random and secret integer k, is this value here. We then end up with an r with an x coordinate of this and y coordinate of this value here. The x coordinate is just this. Then s that we compute is this value, and then the signature ends up being r and s combined. Pretty easy, right? Let's move on to the signature verification. So again, first of all, we check that the signature is valid. Then we compute the inverse of s, calculate u1 and u2, recreate the original point r, and check whether v, which is the x-coordinate of that recreated r, is equal to the original r, which was part of the signature. True and true, this refers to r and s being valid elements or values, and then w is this value here, u1 is this integer value here, u2 is this integer value here, and then the point r, the recreated point r, has this x-coordinate. As we can see from above, this is actually the same integer value, so we have a valid signature. Beautiful. Now that we've created and verified a valid signature using Bitcoin's actual elliptic curve, using an example message and an example private key, we know everything that there is to know about elliptic curve cryptography and how this actually works on the Bitcoin blockchain. This is amazing. To anybody who's made it this far, congratulations, you now understand elliptic curve cryptography. And from here on out, I guess the next logical step would be to fully understand transactions, what transaction types there are, how they work, and then see how all of this is applied to an actual transaction and its byte string. Thank you all for watching, and I'll see you in the next videos.